So one consequence of light refracting or bending as it passes from one medium to another is something called total internal reflection. This is what happens when the angle of incidence is sufficient enough that the light, when it refracts out, actually refracts at something greater than 90 degrees. If we have, like this top image, we have light going from a high N, a high index, to a low N. The light bends away from perpendicular. That's called the normal. It actually bends towards the boundary between the two media. In the second diagram, now we've increased that incident angle quite a bit, and you can see the refracted angle is just barely off of the boundary. We can get to a point where that refracted light is exactly on the boundary. That is called the critical angle. That is where we change from refraction, like in the first two, to total internal reflection, like I'm going to explain in a moment. If now in this last diagram we take that angle of incidence and we increase it even more, now we get the refracted ray actually being reflected inside of the first medium. Substances with the highest indexes of refraction have more instances of total internal reflection than others. If we actually look at the table of indexes of refraction, the two highest ones are zircon and diamond. The fact that diamond has an index of refraction of 2.42 means that a lot of the light that passes into a diamond actually gets reflected inside it before it actually gets to an angle where it passes out. This is why if you're looking at diamond rings, they have a whole lot of small cuts on them to create a whole lot of faces, to create a whole lot of opportunities for total internal reflection. That's probably why ladies like them so much, because they do appear to sparkle, because the light just stays inside and reflects off of the faces. Gentlemen who are trying to cheap out on a ring and buy one that's a cubic zirconium, that is actually a form of zircon, which has quite a high index of refraction, 1.92. So the light does reflect inside a cubic zirconium quite well, not as well as diamond. So this is why some people are able to, and I quote, fake a diamond ring by buying a cubic zirconium, because it has the same effect, it's just not quite to the extent that diamond would be. So looking at some calculations involving total internal reflection, what's the critical angle for a water and air interface? Well, I haven't told you where the light is incident and where it is refracted to, but that's implied in the question. In order for a critical angle or for total internal reflection to occur, we need to have the light going from high N to low N. And I haven't told you the ends of either of these substances, but a diagram is going to help us. So we have an interface, a boundary between water and air. And to be completely honest, it doesn't matter which one is on top, which one is on the bottom, but common sense, if we look at reality, water would be beneath air. First thing we need to do is find the indexes of refraction of each of these substances. Water, when we look it up, 1.33. Air, we look it up, 1.0003. And that alone is enough to tell us whether the light is incident and whether it's refracted. It's incident in the water because water has a higher N. So the light will be shining this way from the water into the air. And because I've said this is a critical angle question, the light gets reflected exactly along the boundary between water and air. Because of this, we know that water is the incident, so water's N will be N1, air's N will be N2. The angles are actually measured from a perpendicular to the medium, to the boundary, sorry. Theta 1, we don't know. We don't know what angle we have to shine this light from the water in order for it to be a critical angle. However, because it's a critical angle, we know that theta 2 is going to be 90 degrees. That's a key thing with critical angle. Critical angle is always reflected exactly along the boundary between the two media. So theta 2 in a critical angle will be 90 degrees. So now we have enough information to actually calculate the critical angle here. Same formula as we've been dealing with, n1 sine theta 1 equal n2 sine theta 2. N1's 1.33. Theta 1 we don't know. N2 is 1.0003. Theta 2 is 90 degrees. We start calculating. There's no calculations we can do on the left. On the right, we can go ahead and calculate sine of 90, which is exactly 1. Again, no calculations on the left, but on the right, we have 1.0003 times 1, which is 1.0003. Our goal is to get theta 1, so we'll divide both sides by 1.33. Divide out the right, so sine of theta 1 is 0.752, 105, 2632. To get theta 1 now, we have to do the inverse sine, the arc sine of 0.752, 105, 2632. And as usual with angles, we go to a whole number, we push that into the calculator, and we get that the critical angle is 49 degrees. So what this means, any light that is shone from water into air at an angle less than 49 degrees will actually pass through the water into the air. If the angle of incidence is greater than 49 degrees, then the light will actually be totally internally reflected inside the water. None of it will pass into the air.